Hi everyone, today I will present my project titled Anomaly Detection for Solder Joints using Beta Variation Autoencoder. And I will start with the motivation for the study, then talk about some related works and the approach itself. Then I will conclude with the experimental results. In electronic manufacturing lines, most of the errors are caused by solder joint errors. And to fulfill the need for that, automated optical inspection devices are used. However, these devices are expensive and they require dedicated hardware. Other than that, uh, in the literature, so there is no public data set, and there are just a few abnormal samples like this one, and plenty of normal intact solder joint samples. Therefore, traditional feature extraction and supervised convolutional neural networks based approaches are not doable. And there are a lot of studies regarding the solder joint inspection, and these approaches mostly use hemispherical or circular RGB illuminator to generate such as color contours to extract some features out of it. And these PET regions are called a region of interests. Then features such as features like color features are extracted from them. Then these features are inputted to a classifier that include bias, multi-layer perceptron on sport vector machines. And in the recent years, convolutional neural network-based approaches are used to both localize and classify errors. So in our approach, we use a variational autoencoder-based approach that estimates probability of occurrence of X, where X is the input image. And at first there is a probabilistic encoder that approximates the true posterior distribution, that is, given the input image X, what's the probability of occurrence of the latent vector Z, and the encoder outputs the mean and variance. Then there is a parameterization trick applied to obtain latent vector Z. Then the decoder basically reconstructs the input image from the given latent vector Z. So in order to train the variation autoencoder, the objective is called evidence lower bound. It basically tells us to maximize probability of reconstructing the X given Z latent vector, and we want our posterior distribution to be as close as to standard Gaussian distribution with zero mean and unit variance. Then we try to find the parameters that are the weights and biases of the network that maximizes this objective. The only difference of the beta variation autoencoder is this added beta term that stands for the KL weight, and it basically finds the balance of the reconstruction loss and learned disentanglement. And we have tested two different anomaly scores for finding anomalies of solder joints. The first one is the reconstruction loss, and it is basically the pixel-wise L2 distance between the input and output images. Then another one is the objective, since the evidence lower bound basically maximizes probability of occurrence of our input image. We use negative of it as an anomaly score, and in closed form it is calculated with this equation. Here is our full model architecture. The first row shows the probabilistic encoder part. It has the convolutional batch norms, convolutional layers, batch normalization, and leaky ReLU. Then some max pooling layers are used to reduce spatial dimension. Then there is this decoder part to reconstruct the input image. Here is a full list of our hyperparameters. Then the experimental results are as follows. The first row shows our input images for the model. Then the second row shows the reconstructed images along with their predicted labels. And for the normal samples, we expect low reconstruction loss since we trained the model solely with the normal samples. And then we expect high reconstruction loss for abnormal samples since they are never seen unobserved samples. Then we have also compared our approach with reconstruction-based models, and such as autoencoder that we have done with ARDA last year. And here are the variation autoencoder-based models for different anomaly scores that I mentioned. And we have achieved the highest score with solely reconstruction loss as an anomaly score for a beta variation autoencoder with 0.75% accuracy. So that this angled representation is achieved when the right balance is found between the reconstruction loss and the regularization term, also known the latent channel capacity. We have tried different beta values, and again the highest accuracy is obtained for beta equals to 3. So we have chosen it. To conclude, we presented application of beta variation autoencoder for anomaly detection of solder joints, and despite the challenging environment due to the varying size and shape of solder joints, acceptable accuracy is achieved for both the IC and non-IC solder joints. Other than that, our method does not require any dedicated hardware such as the RGB illuminator, any feature engineering, or the abnormal samples in training the model. So that's pretty much it. Thank you for the attention.